down at the floor beneath your feet right now. Stomp on it if you want to.
It feels pretty solid.
Yeah, it feels entirely permanent. The walls around you, the air you are breathing, just the sheer mundane predictability of the physical world, it all feels so incredibly stable.
Right.
You operate under this unspoken assumption that the universe has settled into its final form, that the laws of physics are just carved in stone, and while, planets might die and stars might burn out, the fundamental fabric of reality itself is safe.
Which is a very comforting thought.
It is. It is also completely terrifyingly wrong. Reality, as you are experiencing it right this second, is not permanent at all. It is a fragile, temporary state, and it is currently hanging over a cosmic life.
It really is the ultimate illusion of stability.
Exactly. And we're looking at a huge stack of theoretical physics papers today to answer one very specific, highly unsettling question. What is actually going to push us over that edge, and why hasn't it happened already?
And the wild thing is, the realization of just how precarious our existence is didn't come from looking out into the void with a telescope. It came from looking inward.
At the quantum level.
Right, at the smallest, most fundamental building blocks of nature. We are talking about the actual foundation of mass itself. So when the mass of the Higgs boson was finally pinned down at 125.10 gigaelectron volts.
Okay, wait, I need to stop you right there.
Sure.
Because throwing out gigaelectron volts usually makes people instantly tune out. Why do those specific numbers matter to the floor beneath my feet? Like, what is the actual relationship between the Higgs boson and reality ending?
Fair enough. Think of the Higgs field as a kind of, like an invisible cosmic molasses that permeates the entire universe.
We have molasses.
Yeah. As elementary particles move through this field, they interact with it, and that interaction is what we perceive as mass. So the heaviest known elementary particle is the top quark, sitting at 172.76 gigaelectron volts.
Meaning it interacts with the molasses the most.
Exactly. It wades through the molasses with the most difficulty, which is why it is so heavy. But here is the thing. The Higgs field isn't just a passive background. It interacts with itself.
It interacts with itself?
Yeah, we call this self-interaction the quartic coupling.
So, meaning the field dictates its own underlying energy structure.
That is a really good way to conceptualize it. The quartic coupling essentially determines the shape of the vacuum's energy landscape.
Okay.
So imagine a graph that maps out the energy of completely empty space. For decades, we just assumed that zero energy, the absolute lowest possible energy state, was a flat, stable plane. We thought our universe was sitting comfortably at the absolute bottom.
Right, because why wouldn't we be?
Exactly. But when you take the standard model of particle physics and you extrapolate those two specific masses, the Higgs and the top quark, to extremely high energy scales, that self-coupling value doesn't just fluctuate.
It drops.
The math drives it into the negative.
So when you say the math goes negative, you are basically saying the floor we are standing on isn't the bottom floor.
It means that the vacuum of space, the absolute lowest energy state of our universe, the foundation that all chemistry and biology is built on, is not actually the lowest possible energy state.
Wow.
We are living in what theoretical physics calls a false vacuum. Mathematically speaking, there is a true vacuum out there that is vastly deeper, vastly more stable.
And we are separated from it only by a localized temporary energy barrier.
Exactly.
I want to make sure I'm visualizing this correctly for everyone. Imagine your reality is a marble, and it's resting inside a shallow crater on the side of a massive towering mountain.
Okay, I like that.
So because we are sitting at the bottom of this specific crater, everything feels flat, it feels perfectly stable to us locally. We look around and think, hey, we are at the absolute bottom of the mountain.
Right.
But we aren't. We're just caught on a ledge. And thousands of feet below us, there is a much deeper, wider valley. That valley is the true vacuum.
Yeah.
The only thing keeping our marble, our entire reality, from plunging into that valley is the lip of the crater we are currently resting in.
The geometry of your analogy holds up perfectly. But, you have to add the bizarre rules of quantum mechanics to it.
Right, because it's never that simple.
No, of course not. In classical physics, a marble needs a physical push. It needs actual kinetic energy to roll up and over the lip of that crater. If nothing pushes it, it stays there forever.
But in the quantum realm,
particles, and by extension fields, don't actually have to climb over the barrier. Because of spontaneous quantum tunneling, a system can simply transition through a barrier without possessing the energy to climb over it.
it just phases through.
Basically, yeah. It borrows the energy, disappears from the crater, and just reappears on the outside slope, plunging toward the true vacuum.
So at any given moment, the universe could just spontaneously tunnel through the lip of the crater. The floor just drops out from under us without any warning whatsoever.
Yes. A microscopic bubble of the true vacuum would just appear somewhere in space. And because the inside of that bubble is at a lower, more stable energy state than the false vacuum surrounding it, the bubble would instantly begin expanding outward.
Accelerating toward the speed of light.
Exactly.
Okay, let's say you are standing in the path of that bubble. What physically happens to you?
The rules of reality are rewritten at a fundamental level. The properties of the Higgs field change abruptly.
But mass itself changes.
Right. The masses of all elementary particles change. The electrons orbiting the nucleus of every atom in your body would suddenly spiral out of control or just crash inward.
Oh, wow.
Protons would decay. Complex chemistry becomes physically impossible. If that bubble washes over you, the biology that allows your brain to process this exact sentence just ceases to exist.
It is absolute, fundamental erasure.
Complete erasure.
Which sounds completely terrifying. But when you look at the baseline math for a pristine, perfectly empty universe, the probability of this spontaneous tunneling happening is absurdly low.
Very low.
Like, if empty space was just an endless void, the calculations put the spontaneous lifetime of our false vacuum at something on the order of 10 to the power of 100 years, or even 10 to the power of 400 years.
To put that in perspective, the current age of the universe is about 14 billion years.
Right.
10 to the power of 100 is a 1 followed by 100 zeros. It is an unfathomable stretch of time.
So if empty space was all there was, this would just be a mathematical quirk to discuss on a chalkboard. It would be an existential curiosity, but nothing that should ever make you look nervously up at the night sky.
Exactly. But space isn't an empty chalkboard.
No, it's not. The universe is cluttered. It is incredibly messy. It is filled with radiation, matter, and extreme gravity. And that brings us to the core problem with the false vacuum.
Right, because in nature, phase transitions almost never happen completely spontaneously.
That is the critical pivot in this entire field of study. Think about supercooled water.
Yeah, that's a perfect example.
You can chill a bottle of highly purified water well below its freezing point, and it will actually remain a liquid.
Because it is stuck in a metastable state, just like our false vacuum.
It desperately wants to freeze, mathematically speaking, but it needs a catalyst.
It needs a tiny impurity.
Exactly. A speck of dust, a microscopic scratch on the glass, a sudden physical shock. The moment that impurity is introduced, the ice crystal nucleates around it, and the entire bottle freezes almost instantly.
So if our reality is sitting in this metastable state waiting to freeze over into the true vacuum, what acts as the speck of dust?
Right. If dust seeds an ice crystal, what kind of cosmic impurity seeds the destruction of reality itself?
Well, we are looking for a localized region where the geometry of spacetime itself is warped so violently that it cracks the math wide open.
And what is that?
The ultimate cosmic impurity, a microscopic primordial black hole.
Wait, I need to challenge this immediately. A black hole's gravity is so intense it traps light.
Right.
It crushes matter down to an infinitely dense point.
Yeah.
If an incredibly fragile quantum bubble of true vacuum is trying to form, how could a black hole act as a catalyst? Wouldn't the extreme gravity just violently crush the bubble out of existence before it could even expand?
You would intuitively think so, but the mathematics of seeded nucleation reveal a deeply counterintuitive mechanism.
Okay, how so?
To understand how the black hole pulls the trigger, we have to look at why the universe hasn't tunneled on its own. In empty space, for a bubble of true vacuum to form and survive, it has to overcome a massive energy penalty just to exist.
Right, creating the bubble isn't completely free.
Exactly. There are two competing energetic factors. First, you have the surface area of the bubble wall. Creating that boundary between the true and false vacuum costs energy.
It creates a tension.
Yes, a surface tension that wants to snap the bubble shut, almost like a stretched rubber band. But second, you have the volume inside the bubble.
Because the inside is at the lower true vacuum energy state.
Right, which gives you an energy advantage. The larger the bubble gets, the more volume you have, and that negative energy eventually overwhelms the surface tension.
But getting to that tipping point is the actual problem.
Yes. To reach a critical size where the bubble can survive and expand, you have to create an enormous initial volume all at once. The energy penalty to carve out that initial volume of new reality is astronomically high.
So that volume penalty, is what normally stops the quantum tunneling dead in its tracks.
It is the exact reason the universe's lifetime is 10 to the power of 100 years.
Okay, let's ground this with a physical analogy. Imagine you are tasked with hollowing out the exact center of a solid steel sphere.
Okay.
But you aren't allowed to drill through the outside. You have to somehow extract the core from within.
That sounds impossible.
Right. The core is the hardest part to remove because it's completely surrounded, tightly packed by the immense pressure of the steel around it. The sheer energetic effort to carve out that inner volume all at once is staggering.
I see where you're going with this.
So how does putting a black hole into the center of this quantum bubble solve the problem?
The black hole essentially eats the core of the bubble for you.
It eats it.
By definition, a black hole possesses an event horizon, a physical boundary, beyond which nothing, not even light, can escape. When theoretical physicists map this out, the integration for the volume of the true vacuum bubble doesn't start at a microscopic point in the exact center anymore.
Because the center isn't there.
The center of spacetime in that region is literally gone. The integration starts at the surface of the event horizon.
So the black hole has already hollowed out the hardest part of the steel sphere.
Exactly. You completely bypass the astronomical energetic cost required to convert that central volume, because that volume is hidden behind the horizon. It has been physically excised from our observable universe.
Wow. By doing that, the total energy barrier for vacuum decay must plummet dramatically.
It does. The black hole's presence takes the most punishing part of the quantum tunneling equation and just deletes it.
It takes the hardest part of the equation and tears it out of the textbook. But the papers show it gets even stranger than just a volume discount, doesn't it?
Yeah.
We aren't just talking about empty space being deleted.
No, we are talking about the actual geometry of space-time physically contorting around the black hole.
This brings us to a mathematical contortion known as a conical singularity, or a deficit angle.
Right. To calculate these quantum tunneling rates, physicists use a very complex mathematical tool where time is treated as a spatial dimension. It's called imaginary time.
Stop right there. Imaginary time. Are we doing actual physical science here, or are we just playing with theoretical math to force a scary result? Like, what does imaginary time actually mean for the physical universe?
It is a standard mathematical trick used in quantum field theory to make path integrals solvable.
Okay.
By rotating the time coordinate mathematically, oscillating quantum fields transform into exponentially decaying ones, which allows us to actually calculate the tunneling probabilities. In this framework, the geometry around a static black hole becomes perfectly periodic. It loops back on itself smoothly.
But a vacuum bubble expanding isn't static.
Exactly. When a dynamic bubble wall forms, separating our false vacuum from the true vacuum, the geometry demands a different rhythm.
So the expansion of the new reality and the presence of the old black hole are completely out of sync.
The time periodicity of the inner black hole remnant and the time periodicity of the expanding vacuum bubble simply do not match. You have a severe geometric mismatch.
How does that look geometrically?
Imagine a perfectly flat circular pie. Now cut a slice out of it and force the remaining edges together to form a cone. That missing slice is the deficit angle. Space itself is pinched.
But normally, in physics, if you hit a singularity or a pinched geometry like that, it means your math is broken. You've hit an error in your theory.
Normally, yes. But in the context of calculating out of equilibrium decay rates, this deficit angle is not an error. It represents a physical reality of the transition. And mathematically, this deficit angle provides a strictly negative contribution to the total action of the system.
Wait, a negative contribution? Let me translate that. Instead of breaking the physics, this mathematical contortion actively reduces the barrier for vacuum decay even further.
It does. The warping of spacetime doesn't just passively allow the bubble to form. The geometric mismatch actively lubricates the destruction of the universe. It pulls the trigger.
Which naturally makes anyone listening to this look up at the night sky and ask the absolute obvious question.
Why are we still here?
Yes. If black holes are the ultimate cosmic lockpicks for destroying the universe, and we know for an absolute fact our galaxy has a supermassive black hole sitting right in the center of it.
Sagittarius A star, yeah.
Right? Not to mention millions of smaller stellar black holes just wandering around the spiral arms. Why hasn't the vacuum decayed?
Because size matters. The astrophysical black holes you were thinking of, the ones formed from the gravitational collapse of dying stars, are far too massive.
Too massive to be catalysts.
Yeah. Because they are so large, their event horizons are physically immense, spanning kilometers or even millions of kilometers, and conversely, their temperatures are incredibly close to absolute zero.
So they're too cold and too sprawling to trigger this specific quantum effect.
The physical size of the black hole needs to perfectly match the characteristic scale of the Higgs bubble wall. A stellar black hole trying to catalyze the vacuum is like trying to use a giant wrecking ball to pick a microscopic lock. It simply doesn't fit the mechanism.
Okay, so if the massive ones are too blunt, we need a microscopic needle.
Yeah.
But you just said stellar black holes form from collapsing stars, which have a minimum mass limit.
They do.
If stars can't collapse into microscopic black holes, how could a black hole small enough to pick this lock ever exist?
To find a black hole that small, we have to look past the life cycles of dying stars and look all the way back to the incredibly dense, chaotic environment a fraction of a second after the Big Bang.
Primordial black holes.
Yes. These are hypothetical compact objects formed not from collapsing matter, but from the raw, intense density fluctuations of the early universe itself.
The universe was just a dense soup back then.
Exactly. Because they formed before stars even existed, they aren't bound by stellar mass limits. A primordial black hole could be born with the mass of a mountain, the mass of an office building, or even the mass of a paperclip.
And a primordial black hole wouldn't just sit in the void unchanged for 14 billion years. It is subject to Stephen Hawking's most famous discovery.
Yes, Hawking radiation.
Which means they shrink.
Right. Black holes are not entirely black. The intense gravitational field near the event horizon causes empty space itself to spontaneously generate particle-antiparticle pair.
And occasionally one particle falls into the black hole while the other escapes.
Oh, exactly. To the outside universe, this looks like the black hole is emitting a faint thermal radiation, slowly bleeding its mass away into the void.
But here's the exact mechanism that makes Hawking radiation so terrifying in this context. As a black hole loses mass, it does not cool down and gently fade away into nothingness. It is exactly the opposite. Why?
Because black holes have a negative heat capacity.
Meaning, as they lose energy, they get hotter.
Yes. As a black hole shrinks, its event horizon becomes smaller, and the curvature of spacetime at the horizon becomes sharper, more extreme. These tighter tidal forces are much more efficient at ripping those virtual particle pairs apart.
So the smaller the black hole gets, the hotter and more violently it radiates.
It is evaporation in reverse. It is an engine that spins faster and burns hotter the closer it gets to running out of fuel.
So we have this primordial black hole. It was born billions of years ago in the cosmic soup. It has been slowly evaporating this entire time, bleeding mass, getting smaller, getting exponentially hotter.
And as it shrinks, its physical dimensions approach a horrifying mathematical sweet spot. It enters what theoretical physics identifies as the critical mass window.
The needle is finally small enough for the lock.
Exactly. The calculations dictate that when an evaporating black hole reaches a mass exactly between 0.03 kilograms and 0.17 kilograms, which is microscopic, roughly 10,000 to 100,000 times the Planck mass, its physical size flawlessly aligns with the exact width of the Higgs vacuum bubble wall.
It becomes the perfect catalyst. The lockpick perfectly slides into the tumbler.
In that extremely narrow mass window, the severe warping of spacetime is optimally tuned to catalyze the tunneling. At this exact mass, the black hole is incredibly hot. The thermal fluctuations combine with the geometric deficit angle we discussed earlier.
And the decay rate of the vacuum overtakes the Hawking evaporation rate.
Yes. The branching ratio favors destruction. If a primordial black hole reaches this critical size, the probability of it triggering the collapse of reality doesn't just increase slightly, it approaches 100%.
It becomes a mathematical certainty.
Yes.
This leads to the absolute dread of the billion-ton paradox.
Yeah.
Let's do the math on this timeline for a second. Because of the specific way Hawking evaporation scales with time, a heavier black hole evaporates incredibly slowly, while a lighter one evaporates rapidly.
Right. It's not linear.
Any primordial black hole that was born in the early universe with an initial mass of less than 1 billion tons, which sounds heavy but is only about the mass of a small asteroid, would have completely evaporated by today.
And because it would have completely evaporated by today, it would have inevitably, unavoidably, passed through that critical doom window of 0.03 to 0.17 kilograms along the way.
You literally cannot skip past it. As it shrinks down to nothing, it must pass through the exact size of the lock.
You can't avoid it.
Think about the implication of that for you, listening right now. If even a single primordial black hole under 1 billion tons ever existed anywhere in the vast observable universe, it would have already shrunk down to that microscopic catalyst size.
It would have flawlessly aligned with the Higgs field.
It would have triggered a bubble of true vacuum, and that bubble would have expanded outward, destroying all chemistry and physics in its path.
The math governing seeded nucleation is brutal. If the framework holds true, the simple fact that you and I are sitting here breathing, and that the atoms holding our chairs together haven't disintegrated, means that light primordial black holes cannot exist. Period.
There must be a mathematically rigorous upper bound of practically zero on their abundance.
If astronomers ever find observational evidence that a light primordial black hole actually exists, it is definitive proof that the standard model of particle physics is fundamentally incomplete or just completely broken.
We are sitting right in the middle of a mathematical tripwire.
Yeah.
If the equations definitively state that any black hole under 1 billion tons should have already triggered a light-speed bubble of true vacuum, why are we still here?
It's the ultimate question.
Either the universe was perfectly, meticulously swept clean of any black holes below a certain arbitrary weight limit, which feels incredibly unlikely,
Unlikely.
or our understanding of the universe's mathematical defenses is profoundly wrong.
And this is where we see a fierce theoretical debate unfolding in the literature. Because physics is never just about accepting one equation at face value. It is about interrogating the underlying assumptions of those equations.
All right.
The terrifying math we just walked through, the idea that the black hole hits 0.03 kilograms and guarantees destruction, makes one colossal hidden assumption about how a black hole interacts with empty space.
It assumes the black hole is operating in a perfectly sterile environment.
It assumes the black hole is in perfect thermal equilibrium with its surroundings. The entire calculation for the quantum bounce that triggers the vacuum decay relies on a mathematical boundary condition called the Hartle-Hawking state.
Let me make sure I grasp this. The Hartle-Hawking state is a scenario where the black hole is essentially eternal.
Yes.
It is sitting in a perfectly balanced, invisible heat bath. For every particle of Hawking radiation it spits out into space, it absorbs an identical particle of radiation back from the environment. It is static. It is unchanging.
Precisely. It is a mathematical convenience used to make the equation solvable. But an evaporating black hole in the real physical universe is not sitting in a perfectly balanced heat bath.
Of course not. It's violently bleeding energy into the cold, empty void of space and taking absolutely nothing back in.
It is dynamically changing. It is fundamentally out of equilibrium. And when you adjust the boundary conditions to match this realistic, isolated state, what physicists call the unruh vacuum, the entire catastrophic picture shifts.
Because it's not a spherical cow in a vacuum anymore. It's a dynamic bleeding system. And that dynamic state creates a mathematical shield.
We call it the gray body factor. Surrounding a realistic evaporating black hole, there is a geometric potential barrier. It is an inherent property of the intense spacetime curvature immediately outside the event horizon.
And what does this barrier do?
This barrier acts like a strict filter. It significantly suppresses the emission of highly energetic modes.
I want to break down this gray body filter. To force the Higgs field to transition from false to true vacuum, you need a coherent burst of high-energy radiation from the black hole.
Correct.
You need the black hole to pump out the exact right frequencies of extreme heat to build that critical vacuum bubble. But the gray body factor says, no, the geometry of spacetime won't let those specific high-energy frequencies escape.
The space-time curvature actually bends the high-energy modes back into the black hole. They cannot easily propagate outward. The unruh vacuum essentially starves the tunneling process.
So even though the black hole is technically hot enough internally to trigger the decay,
the radiation that actually makes it out into the surrounding vacuum is filtered. The decay probability, instead of exploding toward unity at 0.03 kilograms, remains exponentially suppressed.
the black hole might possess the heat, but the geometry of its own radiation creates a physical wall that prevents that heat from pulling the trigger on the vacuum.
Exactly.
That is a brilliant defense mechanism. But some recent papers argue there is an even deeper layer of protection, because primordial black holes didn't just pop into existence fully formed.
No, they had to collapse from dense pockets of matter in the turbulent soup of the early universe.
Yes, and this is where recent reevaluations of collapsing matter completely flip the paradigm. Theoretical frameworks are moving away from studying eternal black holes, and instead modeling a black hole as it is actively collapsing.
This introduces the erasure of memory. Imagine a sphere of super dense early universe matter intensely compressing inward under its own gravity. As the surface of this collapsing star approaches its Schwarzschild radius, the physical point of no return, the gravitational redshift, becomes extreme.
Let's make sure the redshift analogy is accurate. Redshift doesn't mean things physically slow down like a computer virus over a bad connection. It's about frequency and temperature.
Right.
As light or radiation tries to climb out of an intense gravity well, its wavelength is stretched. As the wave stretches, its frequency drops, which means energy drops. It literally cools down.
That is the exact mechanism. Now map that onto the false vacuum. If a bubble of true vacuum tries to nucleate around this forming black hole, it relies on the intense thermal state of the collapsing matter to provide the necessary activation energy.
But the extreme gravitational redshift at the forming horizon exponentially stretches out that energy.
It fundamentally erases the initial thermal conditions that the matter started with. Any specific, highly energetic state that could have violently seeded the vacuum is stretched out, cooled down, and washed away by the intense gravity.
The heat needed to trigger the vacuum decay is literally drained out of the system by the gravity of the collapse itself.
Yes. By the time the event horizon actually forms, the energetic data of the collapsing matter is so profoundly redshifted, it becomes mathematically impotent.
The calculations reveal that the extreme states required to strongly catalyze the vacuum decay simply do not survive the collapse process.
The saddle point that governs the mathematical decay is dominated by a single, definite energy state that is practically harmless. The forming black hole only weakly catalyzes the decay.
So the entire underlying assumption that small black holes inevitably become explosive lockpicks turns out to be an artifact of using overly idealized eternal mathematical models that ignore the physics of collapse.
Basically, yeah.
Let me synthesize this because the implications are breathtaking. The universe isn't just lucky, it is actively protecting itself.
It appears that way.
The very act of the black hole forming the extreme gravity, stretching wavelengths, and draining away the necessary thermal energy, and the very act of it radiating out of equilibrium, contorts space-time in such a way that it mathematically neuters its own ability to destroy the vacuum.
It's beautiful, really.
As the black hole attempts to reach the physical state necessary to trigger the end of the universe, the relativistic laws of gravity inherently suppress the trigger. It's a built-in cosmic failsafe.
It is a remarkable display of mathematical self-consistency. However, the debate in theoretical physics is far from settled. Some argue these defenses are robust, while others suggest they only delay the inevitable.
But there's a completely separate, even stranger possibility emerging from the literature.
Oh, absolutely.
A scenario where the black hole doesn't just get blocked by a gray body filter or redshifted into impotence. What if the black hole never even reaches that ultra-hot, microscopic critical mass of 0.003 kilograms to begin with?
What if it gets choked by its own data?
This is where we leave the realm of pure gravity and space-time geometry and go full quantum information theory. We have to view the black hole not just as a curvature of space, but as a hard drive.
Right. Every physical object in the universe holds quantum information. But a black hole is a very specific type of theoretical entity known as a saturon.
A saturon, what exactly is that?
A saturon is an object possessing the absolute maximum theoretical capacity for information storage per unit of energy. There is no physical way under the laws of quantum mechanics to pack more data into a confined space than by making it a black hole.
So think about how a primordial black hole forms. Vast amounts of distinct particles, radiation, dense matter, each carrying their own unique quantum state, their own information, are all crushed together.
The black hole encodes all of this immense quantum information into its internal microstates.
And the entropy of the black hole, the measure of that hidden information, scales with the surface area of the event horizon.
Correct. Now, bring Hawking evaporation back into the picture. The black hole emits thermal radiation into space, and as it does, it loses mass and physical size.
According to the fundamental principle of unitarity in quantum mechanics, information cannot be destroyed.
Exactly. Unitarity is non-negotiable. As the black hole sheds its mass and gets physically smaller, it must somehow retain the immense, staggering backlog of quantum information it encoded during its formation.
Imagine you have a computer with a 1 terabyte hard drive, and it is completely 100% full. There isn't a single megabyte to spare.
Okay.
Now, you try to run an incredibly complex uninstallation program to slowly delete the system files and shrink the drive's footprint, but the uninstallation program itself requires a massive amount of free working memory just to process the act of deleting files.
And it doesn't have it.
Because the hard drive is completely jammed with retained data, the computer has no working memory left to execute the deletion. The processes begin to conflict. The processor stutters, the fans spin up, and eventually, the sheer density of the data causes the entire operating system to just freeze.
That analogy perfectly captures the theoretical framework known as the memory burden effect.
The memory burden.
Yes. During the initial phase of its life, the black hole evaporates and sheds mass quite easily, but when it loses roughly half of its initial mass, it forcibly hits a quantum wall.
The bottleneck.
The sheer density of the retained quantum information, those packed microstates, begins to severely backreact on the physical system. The internal state of the black hole becomes so overwhelmingly complex and entangled that it interferes with the quantum modes responsible for generating the Hawking radiation at the horizon.
The black hole literally gets choked by its own data. It reaches half its original mass, and the immense backlog of memory fundamentally jams the mechanism of evaporation.
And the consequences for the universe are profound. The evaporation fundamentally halts. Or, more accurately, it slows down so drastically that it practically stops on any relevant cosmic timescale.
So it stops shrinking.
The remaining lifetime of the black hole no longer follows the standard, fast-paced Hawking timeline where it rushes toward oblivion. It shifts to a highly suppressed power law, locked in by its immense entropy. The black hole basically gets stuck.
So if the memory burden effect is real, the primordial black hole never shrinks down to 0.17 kilograms.
It never reaches the doom window.
It never gets hotter and hotter until it perfectly aligns with the Higgs vacuum bubble wall. Long before it ever gets small enough to pick the lock, it hits this data bottleneck and freezes.
The memory burden effect prevents the black hole from ever becoming a catalyst. Instead, it leaves behind a stable, macroscopic remnant.
It becomes an incredibly entropic, incredibly cold ghost of a black hole that will essentially persist unchanged forever.
Which brings us to an incredible, awestruck implication for you, the listener, and the universe you are living in right now.
Yeah. If these primordial black holes were born in the violent first moments of the early universe, and they didn't evaporate away into ticking time bombs that destroy reality, where are they now?
If the memory burden stabilizes them, millions of these light primordial black holes survive into the present epoch. They would be completely dark. They would be collisionless.
And they would be incredibly massive compared to an atom, but microscopically small compared to a star.
And because they emit almost no radiation, they would interact with the surrounding universe almost exclusively through their gravitational pull.
Dark matter.
They become a leading theoretical candidate for dark matter, the invisible scaffolding of mass that holds every galaxy together.
I want you to really think about that profound irony. The very objects that the math initially warned us were the ultimate cosmic lockpicks, the terrifying microscopic anomalies that should have seeded the destruction of our reality billions of years ago, might actually be the invisible gravitational glue holding the spiral arms of the Milky Way together.
It's crazy to think about.
They are saved from becoming apocalyptic time bombs by their own quantum information bottlenecks. They are frozen into ultra-cold ghosts floating through the universe, floating through the room you are sitting in right now.
It is a stunning reversal of roles. If this theory holds, they transform from the harbingers of a false vacuum transition into the foundational mass that allowed galaxies, stars, and eventually planets to coalesce in the first place.
So bringing this all back down to the tightrope walk of our existence. You stomp on the floor and assume the ground is permanently stable. But we know, mathematically, that the Higgs field is sitting in a false vacuum.
We are hanging over the edge of the ledge.
Based on everything we've pulled from these theoretical papers, there are really only three possibilities for the reality you are experiencing today.
First, the most straightforward, perhaps most boring answer. Primordial black holes below 1 billion tons simply never existed.
The early universe, for whatever complex inflationary reasons, just never produced them. And our reality happens to be completely empty of the ultimate cosmic impurity. We are mathematically safe because the lockpicks were never forged.
Second, they do exist. The early universe was teeming with them. But the profound laws of the universe mathematically protect us from their extreme states.
The out-of-equilibrium gray body factors filtering the heat, the severe redshift of gravitational collapse washing away the initial energy, or the immense quantum memory burden fundamentally choking them with data.
They are frozen, neutered, turning into the dark matter ghosts that surround us safely every day.
But there is a third possibility. one that theoretical physics cannot entirely rule out.
That the original math is actually right, that the defenses aren't absolute.
That the lockpicks exist, and somewhere, deep in the vastness of the cosmos, one of them didn't get choked by data. One of them reached exactly 0.03 kilograms.
If that happened, a bubble of true vacuum was triggered. And if it was triggered, it is currently expanding across the universe, rewriting the laws of physics.
Now, a common misconception is that because this wall of destruction approaches at exactly the speed of light, you would never see it coming.
You wouldn't even have time to register fear. You would just simply cease to be.
But the physics of the expansion are slightly more complex and honestly much more chilling. Because intergalactic space isn't completely 100% empty.
No. Even in the deepest voids between galaxies, space is filled with sparse intergalactic plasma, solitary atoms, stray cosmic dust.
As the true vacuum bubble accelerates outward, expanding asymptotically toward the speed of light, its interaction with this surrounding matter induces a microscopic physical drag on the bubble wall.
It slows the expansion down by just fractions of a kilometer per second below the absolute speed of light.
Which means the wall of destruction is slightly subluminal. It is moving just a hair slower than light itself.
And that slight delay changes the entire ending.
Because of the extreme, violent mismatch in physics, across that expanding wall, the bubble acts like a cosmic snowplow. It would compress and shoot a collimated, unimaginably intense flux of high-energy photons and neutrinos directly ahead of it.
A shockwave of pure energy.
If reality is ending, our final warning won't be an alert on your phone. It won't be a news broadcast. Because the light outpaces the bubble by just a fraction of a percent, the sky will change first.
It will be a blinding, apocalyptic ghost light of decaying Higgs particles and extreme radiation arriving in our sky.
Carrying through the upper atmosphere just years, or maybe even just months, before the physical wall of the true vacuum finally hits the Earth. Sleep tight.